Hello, welcome to Code Design. Today we'll be solving Leetcode 33, search in a rotated sorted array. So we have a sorted array which is sorted descending order, ascending order, and it is also rotated. So what is rotated? If you can see here, 0, 1, 2, 4, 5, 6, 7, and here um, this 0 is going so this 0 is going here, 1 is going there, 2 is going there, so at the end. So the array now we have is 4, 5, 6, 7, and 0, 1, 2 all rotated. It's a left rotation. So after the rotation the array looks like this, and now we have to find out a element in the array. So we are not allowed to do the sequential search, if otherwise it would be very easy just to look through the elements and find the element in on time complexity. But we are not allowed to do that. We have to solve this problem in O log n runtime complexity. So time complexity would be O of log n. So when we say O of log n, then we have to think something like binary search, right? Because that is the one we can get or find something in log n time. But binary search requires the array to be sorted, but our array is not fully sorted. Is sorted, but there is a partition. Like for here, there is a partition here. From 4 to 7, this is sorted. From 0, 1 to it is sorted in ascending order. So we cannot use the regular binary search. We have to do some modification. So we'll be doing some modification binary search to solve it. So one important thing in the binary search is to partition the array in two parts, and whatever is our target element to find, decide which part we'll be searching for. So if this array is a 7 element, so if we take the mid would be index 3, which is this element 7. Then on the right side we'll have 0, 1, 2, and left side we'll have 4, 5, 6. And for this one, when 7 is the middle element, we can see that we get two sorted um, partial array in both sides. This one is one sorted subarray and another sorted subarray is 0, 1, 2. But when we have 6, then this part is sorted 4, 5, but not this part. So our goal would be to find out a middle element, and then find out which part is sorted, this part or that part. So how we can find out which part is sorted? So if our middle element is 7 and we have our leftmost element is 4, so easily we can find it out if 4 is less or equals 7. If 4 is less or equals 7, that means this left side is sorted, including the middle element. And if not, then this part is not sorted, then the other part should be sorted, because the array has rotation, and after rotation, it will be divided into two sorted part. So whatever element we take, um, what actually depends on the element that we select. So whatever element we take, based on that, there will be one part which is sorted. So based on this understanding, let's try to write the code, and we can then look back how we should be coding. Actually, this type of code, you cannot just do it. You need to look at your input to code it. So we initially, our left, we take two pointer left and right. So our left would be 0 and right equals nums dot length minus 1, and while left less or equals right. So this is the condition of binary search, right? Where left is less or equals right. So why equals? Just think about, we need to find out 2, which is the rightmost element. So find out 2, right pointer will still be there. It will not move. It will not move. But initially, left pointer would be this 4, and right pointer will be 2. So we'll have a middle, which is 7. And then our target element does not belong to 4 to 7. So it is not in the range from 4 to 7. So we will move the left pointer to 0. That means mid plus 1. And right pointer will still be at 2. So now from these three element, we need to find the middle element. And then still it doesn't work. So we need to um, um, move the left element, left pointer. So um, the this is how left pointer will finally come to all the way right, and then left and mid would be equal. Sorry, left, yeah, left and right would be equal, and we'll find that too. Actually, mid would be also the same. This is how we will be able to find two. Now that we know that why we need to do less or equals left, what we do in binary search, we find the mid element. We can say left plus right by 2. So we find the mid element, and now what do we check with the mid element? If our leftmost element num of left is less or equals uh, nums. Nums of left is less or equal nums of mid. So we are including mid also. If this 4 is less or equal 7, initially our mid would be 7. If it is, then this side is sorted. So if this side is sorted, we can try to see if our target element within this range. If it is within this range, then we should be able to find the element in this subarray from 4 to 7 if the element exists. So now what we need to check? Our target, right? If whatever is our target is um, greater or equals um, greater or equals nums of left and target is less than nums of mid. So if our target is greater or equals 4 and target um, less than um, mid, then what we do? Then our right, that means target within this range. If target within this range, we don't need to go further actually. So what we can do, we can, and less than mid. This is our mid. So that means target within this. If target is within this, then we can say right equals mid minus 1. So our mid here, um, so right would be here. That would be our right. Else, if it is not within this, what will happen? Then we have one option. So mid would be left would be mid plus 1. So why we are making okay, well, there is yes, left equals mid of 1. So there is one thing, when we find out the mid here, we should check if target equals nums of mid. If target equals nums of mid, we can return mid, the index. So this is how it is covering. So now here, if target greater or equals left and target less than this mid, that means within this, then we make the right here mid minus 1. That means our target element would be here from 4 to 6. Otherwise, we can make left mid plus 1. That means if we make left mid plus 1, right would be still the last element. And we are skipping this one because we are checking it here. So this is good. So this was the option if our left side is sorted. So if left side is not sorted, then what? Our right is sorted. So we can say right is sorted. So we can check if target greater than mid and target less or equals nums of right. So target greater than mid, right? Because this part we already checked. So we need to check if target uh, actually greater than nums of mid. Mid is the index. So if target is greater than nums of mid, whatever value is for nums of mid, which is 0, and target less or equals nums of right, it could be equal, then we search here. What we do? That means within the range 0, 1, 2. If within the range 0, 1, 2, so right side would be fixed, our left side will be moving. So left would be mid plus 1. So mid is 7, mid plus 1 is this 0. So left would be mid, this bound would be here, which is good. And right is already 2. So this is the place we'll be searching from 0 to 2. And if not, what we would do if it is not the case, then our right. So that means we already have a left, and if does not belong in this part 0, 1, 2, then we'll make right part, right is here. So whatever left is here, we'll make right equals mid minus 1. So you can see that since it is not here, so we can easily tell, and it was not also 7 because we have the check here. That means it must be right side must be here. If right here and left is here, or if left crosses right, then actually the element is not in the list. So how do we handle it? We handle it by returning -1. Return -1. So let's verify our code. For this one, again we check mid would be left would be 4 and right would be 2, and mid would be left plus right by 2. That means 3. 0 plus 7 by 2, which is index 3. That means this 7. And if target equals nums mid, no, is false, then we will check nums of left less or equals nums of mid. So if this part is sorted, actually it is, this part is sorted, then we'll check target greater or equals nums of left and target less than nums of mid. That means if target within this, no, our target is 0, is not, then we'll say left equals mid plus 1. So now our left would be this and right is still 2, right didn't change. So this is our search area now, 0, 1, 2. And then we'll come again here. Um, uh, it will find the mid. So this is our 5 and 7. 5 and 7 means 12. 12 by 2 is 6. So our mid would be mm, uh, here 2. And 6, this is index 6, and so target equals nums of mid is true, it will return it. So this is how we can verify it. So, and let's look, looks good to me. Run. Okay, it got accepted for the simple test cases. This is our first test case. So we have another test case here where target was 3. It searched for target 3 and it returned -1 because we didn't find the target. And 1, target is 0. Again, output -1 is not there. So it passed the simple test case. One improvement we could do here for a binary search, or basically when you do a modified binary search, sometimes um, the mid overflows. So you will get out of bound index, index out of bound exception, because the mid will overflow the right. So how to be cautious and not to avoid that thing, right? Left minus right by 2. So this is one improvement. When you deal with binary search or modified binary search, you can instead of use just mid equals left plus right by 2, you can do left plus left minus right, sorry, right minus left by 2, right minus left by 2. So initially our left would be 0. So 0 plus um, 0 plus 6. 6 minus 0 by 2, which is 3. So let's check again. Okay. Now submit. Okay. It got accepted. It passed all the test cases and is very efficient. It took just 0 millisecond. That means less than 1 millisecond. And it beats 100% of the implementations. And memory wise, not very efficient, but yeah, it still beats 9.04% of the submissions. So that's it. So only the thing we need to consider in binary search or um, modified binary search is to look the conditions. So we need to carefully define this boundary of the search. Otherwise, you could face lots of test case fail and lots of issues. So yeah, I hope you enjoyed it. Let me know.